Population 3 එක C පොර වර්ගය. දැන් අපි යන්නේ. දැන් ඉස්සෙල්ලා තමයි චෙක් කරේ A සහ B කියන පොර වර්ග වල බලපෑම වෙනසක් නැහැ කියන්නේ. mu 1 කරගෙන mu 2 සමානයි බිඳුව කියන්නේ. නැත්නම් මොකද අපිට කියන
ඔව්. Asinta Anushika, add your number into the name. Yes, I'm reading it.
Well, good morning. Time is up. So we need to start now. Hope everybody is ready. I think yesterday we completed completed hypothesis testing with respect to testing a population parameter. They are also specifically with respect to the mean. And we went through other supporting theory in sense that say one tail, two tail, there is one-sided alternative hypothesis, and then two-sided alternative hypothesis, or the unidirectional alternative hypothesis, and then bidirectional alternative hypothesis, and then confidence intervals, and thereby having an idea about the true value, plus testing a hypothesis using confidence interval, and advantages of confidence interval approach compared to the test statistic approach. Okay, that is where we stop. And then we started with the case of where sigma is not known. Isn't it? Sigma is not known. And then we said that especially when n is small, we said x bar minus mu divided by s divided by square root of n as a distribution called t. And when it comes to t, we said that it's not just one distribution we are talking about. Different distributions are depending on the sample size, so that we said t distribution is a single parameter distribution, so that this quantity follows the t distribution, well, in exact term, the specific t distribution of t n minus 1. So the parameter is n minus 1, where n minus 1 is the degrees of freedom. Okay. So that critical value now we need to obtain from that t distribution, t n minus 1. So if you identify alpha to be whatever, and this is the critical value, Tc, and then Tc, so this is minus and this is plus. Now, question is that how do you get this critical value? So these critical values, again, theoretically, whenever it is area, you can do it by means of calculating, by means of performing the integration. But as I said that, thanks to people in the past, for this distribution also, area values are available by means of tables. So that by referring to such a table, we can obtain these critical values. Let me share you now that table. Thing is, those who join late will have a problem. See, Right. So this is what you should see. So that you can see half of alpha is on this side and the other half of alpha is on this side. So the critical value is corresponding to this half of alpha. Okay. So remember this critical value here, or the T, in fact, only the positive values are given here. Because obviously no need to have both minus values as well as plus values, so that only this value is given. Okay. Only these values. So table entries are these values. So you can see that values are given for different alpha. Different alpha. Okay, alpha is this side plus this side. So alpha over 2, this critical value is corresponding to alpha over 2, but the alpha over 2 values are given under the heading alpha. Okay. So as an example, if alpha is 0.05, alpha over 2 is 0.025, so that 0.025 values can be read under 0.05 column. So that's what we need to understand. That is what is meant by the heading two-tail table. So what is given here is two-tail table. So as it is highlighted in the illustration, what is given is this value. Okay. The values of T, V, alpha over 2. Okay. Right. So that first thing you need to do is to identify the degrees of freedom, because so many T distributions are there. Each row is corresponding to a specific T distribution. Each row is corresponding to a specific T distribution, because degrees of freedom is 1. Okay, in this case. Likewise, degrees of freedom 2 distribution is given in the second row. Okay, each row refers to separate T distribution. So as an example, suppose sample size is 16. Suppose sample size is 16. What is the degrees of freedom? 15 and minus 1, 15. So that first identify 15. And if alpha is equal to 0.05, column is this, so that the critical value can be read from this point, 2 point, at the intersecting point of degrees of freedom and then alpha. So that's how we find the critical value. Okay. So that rejection rule, when it comes to hypothesis testing, H naught mu is equal, let's say mu naught, HA mu is not equal to mu naught. Not equal to. So that what test do we perform? Two-tail test. Because it is bidirectional, isn't it? Two-tail test. So that we need the critical value from two-tail table. Two-tail table. Right. So as usual, you calculate the quantity x bar minus mu naught using hypothetical value s divided by square root of n, and then this statistic, sorry, that's right, this statistic is having n minus 1. Because of that, we call this quantity to be T statistic. Okay, T statistic. That's how it is called. Remember, yesterday we discussed Z statistic. Now it is T statistic. Why? Because this statistic follows what distribution? Why do we call it statistic rather than quantity? Is because this is using hypothetical value, isn't it? Using hypothetical value, or using the null hypothetical value, we have calculated the quantity. Because of that, we call this quantity to be a statistic. Okay. So this t statistic follows this distribution, so that the rejection rule is that if t in terms of absolute value is greater than t alpha over 2 n minus 1. This is the critical value corresponding to alpha, but it is two-tailed. It is corresponding to alpha over 2. Reject H naught and then do not otherwise. Got it? Right. Let's have an example. Let's say y bar is 120 and S is 50, N is 15, and then test H naught mu is equal 130 versus HA mu is different from 130. And let's say alpha is 0.05. Right. First thing is what? Calculate the t statistic is given by y bar minus mu naught, null hypothetical value, divided by S divided by square root of n. Let's substitute values. 120 minus mu is 130. S is 50 divided by square root of 15. To make it easy, shall we make n to be 16? So 16. So what we have is that minus 10 divided by 50 over 4. Which is equal minus 10, 12.5. Minus 10, 12.5. So that we have minus 4 over 5, which is minus 0.8. Now, the critical value from the table. T alpha over 2 n minus 1, which is T 0.025, 15. Now, let's get that value from the table. Corresponding to 15. Ah, okay. Same as exactly what we discussed earlier. Remember? So now what is the value? 2.131. Is everybody okay with reading the table? Well, I hope so. So since what we want is alpha over 2, this value is read under 0.05. That is what you need to notice. Okay. 2.131. Get back to is 2.131. And then now, since t in terms of absolute value, which is minus 0.8 in terms of absolute value, is 0.8 is less than t 0.025, 15, which is equal 2.131. H naught is not rejected. Thereby, it is concluded, thus there is no evidence to conclude that true mean is different from over 130. Okay. So that true mean is 130. Got it? Right. And then confidence interval based on t distribution. Then what we have is y bar plus or minus y bar plus or minus t alpha over 2 n minus 1 times s divided by square root of n is how you get the confidence interval. So for the previous example, we substitute values for the example, that is previous example. We have what y bar was how much? Y bar was 120. Plus or minus t value was, since we got the t value, 2.131. 2.131. And then S I gave as how much? S was S is 50. S is 50. 50 divided by square root of 16, right, which is 120 plus or minus 2.131. This was 12.5. 12.5. So 120 plus or minus, can somebody tell me this value? 2.131 times 12.5. Where is Uthman sir?
Okay, sir, give me a second.
Yeah.
It is a 26.64.
Point
64.
64. That's right. That's enough. Thanks. So then 120 minus 26.64. 120 minus 26 is 94.
93.36.
Yeah, that's right. 93.36 to 146.64. So that I am 95% certain that true mean is between 93.36 to 146.64. Isn't it? Remember, same as yesterday. But I want you to notice something here. Now see, we are continuing with the previous example. So in the previous example, did we reject the null hypothesis? No, we did not reject the null hypothesis. You see, H naught is not rejected. Right? H naught is not rejected. And what was our null hypothesis? 130. Now look at the interval that we have constructed. Look at the interval that we have constructed. It goes from 93.36 to 146.64. So you can see 130 is included, which was our H naught value. See, 130 is included. And remember, we discussed that testing hypothesis using confidence interval. So all what we have to check is that now you can see it is consistent, isn't it? The null hypothesis value is included in the interval. That's why it happened to be like we did not reject the null hypothesis. So that you can see all what we have to do when it comes to testing hypothesis using confidence interval approach is that whether the null hypothesis value is included within the interval or not. If it is included, we do not reject the null hypothesis. And if it doesn't include, or if it is not included, then we reject the null hypothesis. Right. So about confidence interval. And mind you, well, with the t-test also, t-test. See, now remember what statistic we calculated? T statistic. Because of that statistic is the one that we calculated. Because of that, the test that we perform is called t-test. The test that we perform is called t-test. So what we have done is that we have performed t-test. So this t-test could be one tail as well. Now remember one tail and two tail. The example that we had was two tail. Otherwise, it is possible H naught mu is equal mu naught, and then HA mu is greater than mu naught. If this is the case, then the test is one tail test. In that case, what is the rejection rule? What is the rejection rule? Rejection rule is if T in terms of absolute value is greater than T alpha n minus 1. Notice that. Earlier it was what? T alpha divided by 2. Now it is T alpha. Reject H naught. And then do not. Otherwise. That's it. And then the question is that, say for instance, if n is equal, example, n is equal 16. So that degrees of freedom is 15. Now the question is that how much is T15? 0.05. Sorry. Let's see how we can read that value from the table. Right. Now the table that we discussed gives the two tail values, isn't it? So that if alpha is 0.05, each side we have alpha is 0.05, so that each side we have 0.025. Now what we want is one side. So now this is what we want. 0.05. One side 0.05. Okay, this is the value we want, the alpha. And I suppose you can understand this is equal to, if we have here in this one, alpha is equal 0.1. Isn't it? If you take alpha to be 0.1 on one side, how much do we have? Half of that is 0.05. Is that clear? What we want is value corresponding to 0.05. And the table gives always what? Value corresponding to half of alpha. So that if we take alpha to be 0.1, half of alpha becomes 0.05. Got it? Because of that, by referring to the table with the heading, column heading, 2 times of alpha, 2 alpha, we can get the required value. By the way, now you see, compared to T alpha divided by 2 and T alpha, which value is larger? T alpha or T alpha over 2? T alpha accommodating more area means closer to 0, meaning T alpha is smaller than T alpha over 2. Okay, so keep that in mind. Keep that in mind. Why? Because then you know when you have the two values, whether the value that you have read is correct or wrong. Now T alpha should always be smaller. So if you happen to have that value to be larger, then you know something's wrong somewhere. Okay, right. Let's get back to the table. Right. Now what we want is one side 0.05, So that what we have to refer to is column heading 0.1. Okay. Column heading 0.1 corresponding to 15. Now you can see that the value is how much? 1.753. Isn't it? 1.753. And earlier, how much was that? 2.131. So that now you can see 1.753 is smaller than 2.131. Correct? So this is how you read the table. Mind you, alpha is not always 0.05. It may be 0.02, 0.01, or otherwise 0.1. It could be any value, but according to whatever the value, using the table, you should be able to read the value. But of course, from this table, you can have alpha to be 0.02, 0.01, 0.02, 0.05, 0.1, 0.1, 0.4 only. Of course, you can refer to more detailed tables. And the other thing is that these days, remember, when you start using computers, statistical software, then what you have is this exact probability. Now remember, using probability, deciding whether the null hypothesis is rejected or not, we discussed yesterday. So using same approach, you can decide. Now the test that we perform is t-test. And then once we have the p-value, looking at the p-value, you can decide whether to reject the null hypothesis or not. Right, so this is about one-tailed test. One thing is, mind you, statistic, whether it is T or Z, remember T, y bar minus mu naught, h naught value. Okay, divided by s divided by square root of n. Not mu naught minus y bar. Okay, because depending on that, the sign varies. Depending on that, the sign varies. Sign is important not to decide whether the null hypothesis is rejected or not. Why? Because there what we are considering is in terms of absolute value. But the thing is that when it comes to interpreting the results ultimately, to conclude whether especially when we reject the null hypothesis, in order to say the population mean is less than the null hypothetical value, or otherwise greater than the null hypothetical value, the sign is important. Because from the sign, then you know whether the sample mean is smaller than the null hypothetical value or not. Isn't it? Because according to that only, you can say that whether the true mean is smaller than the null hypothetical value, or otherwise true mean is greater than the null hypothetical value. So that, remember, otherwise you keep it in mind. So that chance of making a mistake is less. Otherwise, of course, ultimately it is absolute value. But the thing is that, remember, the formula is of this form, because ultimately it could be useful because chance of making a mistake is less. Otherwise, you need to look at the sample mean value and then the null hypothetical value. And after that only you can decide whether to reject the null hypothesis or not. Sorry, whether the null hypothetical true value is smaller than the null hypothetical value or not. But if you have it, have the t statistic after using the formula in the correct way, or substituting the values in the correct way, then simply by looking at the t value, you can decide whether the null hypothetical value is whether the true value is greater than the null hypothetical value, or the true value is smaller than null hypothetical value. Right. So that's about testing the population mean. Okay. Similarly, one might be interested in testing population variance. Population variance. So that H naught as usual, sigma square is equal to, let's say, sigma square 0. Okay. And then HA, sigma square is different from sigma square 0. This time, the principle we use is n minus 1 s square divided by sigma square is having distribution called chi-square. Chi-square distribution. Chi-square distribution. Chi-square is also chi-square distribution. Is in fact this kind of a distribution. Starting from 0, going up to plus infinity. So no minus values are there for the okay. No minus values are there for the chi-square distribution. Goes from 0 up to plus infinity. And chi-square distribution is also single parameter distribution. Single parameter distribution. And the parameter is, again, the degrees of freedom, which is n minus 1. Let me first share the chi-square table. Right. So this is how it looks like. Okay. So the table entries, the values that you read are pretty similar to the values that we read from the T table. Now see, compared to Z table, the table entries in the T table and then the chi-square table are different. Now Z table, what was the purpose? Purpose was to read the probability values. Purpose was to read the probability values corresponding to different Z values. But in the T table and the chi-square table, the table entries are the critical values. What we read from the table are the critical values or this axis values or the chi-square values. Or in the T table case, T values. What we read are the T values corresponding to different alpha. Okay. So it's like completely other way around. So that the T table and then the chi-square table are presented of the form to facilitate hypothesis testing. Because when it comes to hypothesis testing, what is important is the critical value. So that it's very easy to read the critical value from the T table as well as from this table. Right. As an example, suppose the degrees of freedom is 15. As usual, from the first column, you find the degrees of freedom. And then from the other columns, you find alpha. And remember, the table is such that the whole alpha is on one side. Whole alpha is on one side. So that's how we have. Okay. So if you want one tail value, whole alpha is on one side. So as an example, alpha 0.05 and then degrees of freedom 15. So that the value is 24.996. Okay. Keep that in mind. That's how you read the chi-square value from the table. So now let's get into the test. Let's have an example. Example. H naught. Sigma square is 100. Sigma square is 100. And then HA, say sigma square is greater than 100. If that is the case, one tail test. Isn't it? One tail test. Let's say S square is 120. And then N is 60. So let's now calculate the distance. By the way, let's complete this one. That one here. Now remember with chi-square also, you can see it's not just one distribution we are talking about. So many distributions are there, and distribution vary depending on what? Degrees of freedom. So remember, so this here also, this quantity has the distribution chi-square n minus 1. Chi-square n minus 1. N minus 1 degrees of freedom. Okay. Right. So the critical value when we want, critical value has to be obtained using the distribution corresponding to the degrees of freedom n minus 1. Right. Because this quantity is having chi-square distribution, when we replace sigma square by the null hypothetical value, the statistic that we calculated is also termed as chi-square statistic. So chi-square statistic. So statistic is denoted as x square. In fact, x square, this, well, chi is like this, chi square. Okay, chi is actually a lowercase letter from Greek alphabet, and then the uppercase is x. Because of that, we use for the test statistic uppercase value x square. X square is n minus 1 s square divided by null hypothetical value sigma naught square. Null hypothetical value. Let's substitute values. 15 s square is how much? 120 divided by is 100, which is 15, 150, 180, 18. Then x square is 18. Now we know this has a distribution. So we need to compare this with chi-square 15, 0.05. Chi-square 15, 0.05 is how much? Shall we get that value from the table? 15, 0.05 is 24.996. $24.996, isn't it? That's right. 996. So what do we do now? Since x square, which is 18, is less than chi square, 15, 0.05, H naught is not rejected. H naught is not rejected. Thus, there is not enough evidence to say that sigma square is different from 100. Okay, so that we take it as sigma square is equal to 100. Is that clear? Well, when it comes to the chi-square test, as you can see, suppose we have this to be the previous example. The time s square was how much? S square was 120. S square was 120. Suppose we had it like S square is 80. S square is 80. And then n is equal 16. H naught sigma square is equal to 100. And then HA sigma square is different from 100. Yeah. So that two-tailed test. Okay, two-tailed test. If that is the case, what we will have is statistic. X square is n minus 1 s square divided by sigma square. Sigma naught square is 15, s square is now 80, and then sigma naught square is 100. Okay. 100. Now, what we have is 15, 8, 120 is 12. It's 12. Well, now if you can remember, now when it comes to t-test, especially two-tailed test, we have a critical value from left-hand side as well as from right-hand side. And there, interesting thing is that distribution is symmetric, isn't it? Distribution is symmetric. When the distribution is symmetric, when you have the right-hand side value, you can always work out the left-hand side value. Isn't it? Left-hand side value is minus of the right-hand side value. Or otherwise, right-hand side value is minus of the left-hand side value. Because this side value is negative. Isn't it? Minus of negative value is positive. Exactly. It was exactly minus of the other side value. One side value is one side. The critical value of the left-hand side is minus of the critical value of the right-hand side. Or otherwise, critical value of the right-hand side is minus of the critical value on the left-hand side. That's how we have. Why? Distribution is symmetric, number one. Number two, it is symmetric around 0. But chi-square distribution is not symmetric. Number one, it's not symmetric. And thing is that it is starting from 0 and is going up to minus infinity. Sorry, plus infinity. That's how we have. No negative values. So now you can see that by having the right side critical value, CR, you cannot find CL. Okay. From the right hand side value, you cannot find the left hand side value. Correct. So you need to read the left tail value, left tail value. Left tail value separately from the table. Okay. Right. Now the question is that how do you read this value from the table, left tail value from the table? The table gives always this area. So that if you want corresponding to 0.025, how much is this area? Is 0.975. So it is corresponding to then this area 0.97. That clear? Right. Now, in this case, in fact, what we want is the left tail critical value. Why? How do you know that? Okay. Right tail or the left tail? Well, this issue is there with the Z test and T test also, but remember, I describe it of the form, or I discuss the strategy of in terms of absolute value. When you discuss it in terms of absolute value, this issue does not arise. Okay, so it's very straightforward. But when it comes to performing this chi-square test, you find that you cannot escape from this issue as the way we escape with t-test and z-test. Right. So first deciding whether you need left tail value or otherwise right tail value. Okay. Principle is that you find something called expected value. Something called expected value. Expected value is nothing but mean. Long-term average. Long-term average. Expected value of a variable. Okay, expected value of a variable. This is an A side. Okay. Okay, so this is not something exactly related to the chi-square test. Expected value of x is nothing but the mu, the mean. Okay. And then according to the properties of expected values, expected value of ax is a times expected value of x, can be written as a times mu. What is mu? The mean. Similarly, expected value of A1 x1 plus or minus A2 x2 is equal to expected value of A1 x1 plus or minus expected value of A2 x2. Okay. If it is plus, you use the plus sign. If it is minus, you use the minus sign. Okay. Well, here if you want, you can write this as A1 expected value of x1 plus or minus A2 expected value of x2. Is that clear? Maybe example, expected value of 5x1 minus 2x2 is equal to 5 times expected value of x1 minus 2 times expected value of x2, which is 5 mu1 minus 2 mu2. Exactly. If this is minus, here also it is minus. In case if this is plus, here also it has to be plus, here also it has to be plus. Got it? Right. And then now, expected value of pi square n minus 1. Mean, obviously, we have this kind of a distribution. These are the values. This value this many times, this value this many times, this value this many times, likewise. Okay. Now remember, this distribution is what? Relative frequency distribution. Now, those things we discussed quite some time back. So that from those values, we can calculate the mean. So that is what is called expected value. Well, it is found the mean to be equal to n minus 1. Okay. Found to be n minus 1. So that now so that when it comes to testing hypothesis, if x square is greater than expected value of pi square, n minus 1, right tail critical value should be if x square is less than expected value of pi square n minus 1, then left tail critical value should be used. Okay. Keep this in mind. Now, first example. First example. How much was that? 24, sorry. X square was 80. X square was 80. Now, what is the expected value? Expected value? Degrees of freedom is 15. Is 50. This value becomes the expected value. So that now we can see x square, therefore, x square is greater than the expected value of pi square n minus 1. Therefore, what we want is right side critical value. Right hand side. And now what we have is x square to be 12. 12 is x square equal 12 is less than expected value of pi square 15. Therefore, what we want is left-hand side critical value. Okay. So that the rejection rule is that what? Then the rejection rule is hence if x square is less than pi square 0. Left-hand side critical value. Okay. Left-hand side critical value. Pi square left n minus 1. I wrote it as left. Reject h naught and then do not otherwise. When it comes to chi-square test, usually we perform one tail test, which is using the right tail, the right hand side critical value. But for testing, when it comes to testing population variance, of course, you can have both ways, left hand side as well as right hand side. Okay, right now question is that how to read that the critical value from the table. Now let's get back to the table. This is how we have. Now you see 0.025 on the left hand side area, so that the right hand side area becomes 0.975. So this is the one. This is the one. So the critical value corresponding to 15 is 6.262. 6.262. Okay. Right. So that how do you find it now? Pi square 0.975 15 is 6. What was that? 6.262. 6.262. Therefore, x square, which is how much is that? Was it 12? Huh? 12. That's right. Here. Pi square 12. So that now if the calculated value is smaller than the left tail critical value. Now is it smaller? No, it is not smaller. Okay. Since x square is 12 greater than pi square 0.975 15, which is 6.262, h naught is not rejected. Therefore, no or not enough evidence to say sigma square is different from how much? Different from 100. Okay.
Hello, sir. Excuse me,
Quickly.
sir.
Yeah.
Sir, how to calculate the other critical value as 0.975? Can you explain again?
Told you from the table. Is that clear? From the heading, you select 0.975. Is that clear?
Yes, sir, but other critical value is 0.05.
0.05 because that time we perform one tail test. Is that clear? That time I showed you how to perform one tail test. This time I'm showing how to perform two tail tests, especially using left tail critical value. Thank you for asking that question. Is that clear?
Yes, sir.
Not, I don't know. Are you sure that you are okay? Because that time, if you can see that the see, can you see that? Can you see that? Who was it?
Yes,
What is what? Sorry, whoever. That's okay. So that time we perform one tail test. That's why we refer to 0.05, not 0.025. Is that clear? Say yes.
yes, sir, yes.
Okay, thank you. Thank you. Right. Okay. Hope hope it is clear to everybody. Okay. Right. And then I think I need to get back to the screen. Right. In fact, we can construct confidence interval also for sigma square. And see, so that if this is left tail critical value, right tail critical value, CL, CR, probability phi square, n minus 1 greater than equal to phi square L n minus 1 less than equal to phi square right n minus 1 is how much? The chi square between these two is 0.95. So that 95% confidence interval is then chi square L n minus 1 let me write this as x square phi square r n minus 1. And x square, of course, it is n minus 1 degrees of freedom. N minus 1. So and remember, x square n minus 1 s square divided by sigma square is having phi square n minus 1. Okay. So that this can be replaced by x square can be replaced by this, so that we can have phi square L n minus 1 greater than equal to n minus 1 s square sigma square less than equal to phi square r n minus 1. Okay. If you take the inverse of this, taking inverse, we have 1 over pi square L n minus 1 sigma square divided by n minus 1 s square, and then 1 over pi square r n minus 1, isn't it? When taking when taking the inverse, this sign reverse, isn't it? This sign reverse. Okay. So that we will have sigma square, and taking the other two onto the right hand side, n minus 1 s square divided by pi square L n minus 1 greater than equal to n minus 1 s square divided by pi square r n minus 1. Okay. And this may be written as, which is equivalent to n minus 1 s square, taking this onto the other side, s square pi square r n minus 1 greater than less than or equal to sigma square less than or equal to n minus 1 s square pi square L n minus 1. Thereby you can construct the confidence interval. Okay. Homework, s square 300. N is equal 21. Test H naught sigma square is equal to 150 versus HA sigma square is greater than 150. Question number 1 and part 1. Part 2. Test H naught sigma square is equal 150 versus HA sigma square is not equal to 100. Part 3. Construct 95% confidence interval. For sigma square and interpret the results. Ready? You see, these tests are quite important. I mean, real world situation, you need to know, for instance, rainfall variability in a certain area is different from what is expected earlier, because according to that, you need to do the planning. So you need to actually test and see whether the variability is different or not. So you study it and then see that whether variability is different, so that you can do the necessary planning. High variability. Not only that, we are interested in testing the mean. See, testing the variances also you might find sometime to be useful. Okay, so good example is, let's say, rainfall. Otherwise, income disparity. Whether the income disparity has increased or not due to social changes. See, due to COVID. Then you are interested in whether that has happened. So that, we need to attend to that. See, unless we know that, we cannot address the problem. So first we need to identify the problem. So in order to identify the problem, you need to perform this test after having the data. Ready? Right. So that's about inference. Inference. See the word? Let me first complete that sentence. So what we discussed was, it's about making inference with respect to variance. It's the variance. I'm making inference. Now you see, remember the very first day I used the word inference, I said that later on you will have the exact meaning. I think on that day, we simply went by the equivalent word conclusion. Making inference. Now you see, we are making conclusion about what? The population variance, but what we have studied is only sample. From the sample, what we have is only the sample variance, isn't it? From the sample, what we can have is only the sample variance. But using sample variance, now we see we are making a conclusion for the whole population variance. That is what is meant by making inference. That is the difference between inference and conclusion. Applying the conclusion into a wider extent or bigger extent, the whole population. That is what is meant by making inference. Okay. So now we have gone through studying population mean and studying population variance. Got it? But remember, for all these, you need to satisfy the assumption normal distribution. This chi-square test is also valid if normal distribution exists for the data only. So keep that in mind. Right. Next. Comparison between two population means. Earlier we were talking about one population mean. Next is what? Obviously, comparing two population means. We are talking about, let's say this is one population, mean is mu1, variance is sigma 1 square. Second one, mu2, variance is sigma 2 square. We are interested in what? Whether the two population means are different or not. Whether the two population means are different or not. So what is the simplest null hypothesis that we can think of? Simplest is mu1 is equal to mu2. Isn't it? Simplest is this. Otherwise, if you take, otherwise, mu1 minus mu2 is equal to what? 0. If mu1 is equal to mu2, the difference is 0. Okay, our interest is what? Comparing the two. One might think of having the difference 5. Question is, why exactly 5? Why exactly 10? Likewise. Okay. That's why I said the simplest. But there could be requirements. What we want is whether the mean difference is different from 5. Yeah, that's fine. If that is the case, you can have it of that form. Okay, so let's start with objective is to what? Compare the two so that we can have it compare the two. Let's say we have no idea whether the two population means are different or not. So first thing we need to know is that whether the two population means are different or not. If the interest is population means are different or not, then null hypothesis is what? The difference is 0. Okay. So alternative is then opposite of this is mu1 is not equal to mu2. Or mu1 minus mu2 is not equal to 0. Now recall the test that we discussed. Maybe general case T is equal what? Remember what we had? X bar TO is it? X bar minus H naught divided by S divided by square root of N. What is it? X bar is the estimate. H naught is about what? Mean. Estimate minus null hypothesis divided by standard error of estimate. Remember? What is this? This is the standard deviation of X bar, which is called standard error of X bar. Standard deviation of X bar is termed as standard error as well. Remember, we discussed. So this is actually the general formula. The formula is always of this form. Now, if you can see Z test, T test, exactly the same format we followed. Estimate minus null hypothesis divided by standard error of estimate. Right. Now, this is what we are taking into consideration. What is the estimate? What is the estimate? What are we interested in? H naught is what? H naught is mu1 minus mu2. Mu1 is equal to mu2. It means mu1 minus mu2. Whenever we want to compare, what do? Whenever we want to compare, suppose whether two students have same amount of money or not, what do? We actually take the difference in it. Amount of money per student is having, and then from that you subtract amount of money the second student is having, or other way around. We take the difference. Whenever we want to compare, we take the difference. Isn't it? So that we can formulate it of the form mu1 minus mu2 is equal to 0. So, right, mu1 minus mu2 is what we are interested in, and according to the null hypothesis, it is equal to 0. This particular example. So, what is the estimate of mu1 minus mu2? Mu1 minus mu2 is, now what is the estimate of mu? Is a sample mean. Estimate of mu is sample mean. So that estimate of mu1, you can denote it as y1 bar. And estimate of mu2 is what? y2 bar. We can denote it that way. Meaning, from this population, you will have a sample of which the mean is y1 bar. From this population also, you have a sample of which the mean is, let's say, y2 bar. Isn't it? Simple. So clear? So then, what is our estimate? Y1 bar minus y2 bar. What is our H naught? mu1 minus mu2. So according to this is equal to 0. But otherwise, it is mu1 minus mu2, whatever the value. Okay. So I said that sometime you can have the interest, and it is not, the interest is not to study the difference between the two means, because it's possible it's well established. It's possible it is well established that the two are different. But thing is that suppose one machine is producing one machine is producing more than the second machine. One machine is producing more than the second machine on average. But the thing is that we want on average the difference to be more than 5. Then only it is profitable. Of course, producing more, naturally the machine cost, the price of that machine is higher. So we are interested in whether the difference is more than 10 or not, because it's possible if the difference is more than 10 only it is profitable. Otherwise, it's not profitable. Is that clear? So this time we are not interested in whether the two means are same or not, but that is well established. One machine is giving higher value. That is very, but thing is that whether the two main difference is 10 or not is what our interest is. In that case, this becomes not 0, something like 10. Is that clear? So keep that in mind. Right. So this is about this part. E estimate minus H naught. And then what we want is standard error of estimate. What is it? Y1 bar minus Y2 bar. So that if we have the exact value standard of Y1 bar minus Y2 bar, then this test statistic is Z. Then the test statistic is Z. Okay. So now the question is that how much is standard error of Y1 bar minus Y2 bar? Now this we can know from the sample, and this we will know from what? Null hypothesis. So the question now is that this one, standard error of Y1 bar minus Y2 bar. Okay, what do you mean by Y1 bar and Y2 bar? Like now you see, we said we have population 1 and population 2. Taking a sample mean X1 bar or Y1 bar. And then from this also take a sample Y2 bar. But is this the only sample that we can have from this population and this population? No. We can have many more. Another sample. From here also another sample. Okay. So that you can say first population, first sample mean. Second population, first sample mean. And then first population, second sample mean. And then second population, second sample mean. Second population, third sample mean. First population, third sample mean. Likewise, we can have large number of sample means. Our interest is what? Y1 bar minus Y2 bar. So that Y11 minus Y21. And then Y12, Y22. And then Y13, Y23. All those are estimates of mu1 minus mu2. Y11 bar minus Y21 bar is the estimate of mu1 minus mu2. Y12 bar minus Y22 bar is also an estimate of mu1 minus mu2. Y13 bar minus Y23 bar is also an estimate of mu1 minus mu2. So with repeated sampling, we can think of what then? First difference, D1, second difference, third difference, likewise. So we can study a distribution of these differences. Isn't it? Distribution of those differences. What is our x-axis? Is y1 bar minus y2 bar. Distribution. This difference will also be of the same shape. Why? Now remember, we discussed about sample mean difference. There the argument is that most of the time we will have sample mean from the middle area. Because of that, mean of the sample mean is also, or most of the sample mean will also from the center area. Because of that, center area, the frequency is higher, and then the other areas, frequency is smaller. Remember, same argument here also, you will find it to be of the form, since most of the time from the middle area. So you will have in the middle area frequency to be higher, and then the other areas frequency to be smaller. So this we can say mean of y1 bar minus y2 bar. Okay. So the now the axis is y1 bar minus y2 bar. Okay, now this mean. And similarly, we can say variance of y1 bar minus y2 bar. Isn't it? Mean and the variance. Mean of the sample mean differences. Variance of the sample mean differences. Isn't it? Right. Now remember we discussed expected values. Value of y1 bar minus y2 bar. Is what? Expected value of y1 bar minus expected value of y2 bar. Expected value of y1 bar is mu1. Expected value of y2 bar is mu2. See, expected value y is also mu. Expected value y bar is also mu. Remember we discussed this earlier, okay? Under sample mean distribution. I showed you taking an example also. I think I gave a homework also. Hope everybody did that homework. Right. Not only expected value with respect to the mean, but variance can also be worked out. Now we are interested in variance of y1 bar minus y2 bar. But before getting into that, let me discuss about properties of mean, or sorry, properties of expected values, properties of variance. Let variance of x is sigma square. Then variance of ax is equal to a square times variance of x. Variance of a1x plus or minus a2x x2 is equal to a1 square variance of x1 plus a2 square variance of x2. Why? Because we are squaring the coefficient. Squaring the coefficient. Ready? Right. So that variance of y1 bar plus variance of y2 bar. What is variance of y1 bar? Sigma 1 square divided by n1. Remember? Sample mean distribution, variance of Y is sigma square divided by n. So that y1 bar can be denoted as sigma 1 square divided by n1 plus sigma 2 square divided by n2. But mind you, provided y1 bar and y2 bar are independent. Okay, right. But here the consideration, here the consideration is that, remember, go to the first population and take a sample, and go to the second population, take a sample. So that a value that we observe for a unit in the first sample has absolutely nothing to do with value that we observe for a unit in the second sample, isn't it? Because we take the two samples completely independently. Did everybody get that? Since we take the sample completely separately, a value that we observe for a unit in the first sample has absolutely nothing to do with a value that we observe for a unit in the second sample. Isn't it? Because we take the two samples completely separately. So that we can take it as the sample mean is independent from the second sample mean. It's absolutely nothing to do with second sample. So that variance of y1 bar minus y2 bar is sigma 1 square
Recording
divided
in
by
progress.
n1 plus sigma 2 square divided by n2. Therefore, standard error of y1 bar minus y2 bar is square root of sigma square y1 bar minus y2 bar. Now by substituting, therefore, Z is equal y1 bar minus y2 bar minus mu1 minus mu2 divided by square root of sigma 1 square divided by n1 plus sigma 2 square divided by. This follows what distribution? Is a distribution. Got it? So that as usual, if Z in terms of absolute value is greater than Z alpha over 2, reject H naught, do not otherwise. Or if Z is greater than Z alpha, reject H naught and do not otherwise. Is everybody with me? What is this? One
Yes, sir.
tail. Sorry. This is two tail test. This is one tail test. See? I think this is very straightforward. Homework. Y1 bar is equal 60. Y2 bar is equal 75. Sigma 1 square is 125. Sigma 2 square is 180. N1 is 20. N2 is 25. Test H naught. Mu1 is equal to mu2 versus HA. Mu1 is not equal to mu2. Test H naught. Mu1 is equal to mu2 versus HA. Mu1 is less than mu2. 3. Test H naught mu1 is sorry. Mu1 minus mu2 is equal to 5 versus HA mu1 minus mu2 is not equal to 5. Just a minute. Mu2 minus mu1. Why? Because now you see indication from the sample mean is that what? From this, it is like possibility is mu1 is less than mu2. Okay. So that's why I made it this way. Otherwise, this should be minus 1. Right. Confidence interval for mu1 minus mu2. What is the general formula? Again, estimate plus or minus t alpha O2 n minus 1 standard error of x bar. Remember, this is the general formula. So that by applying this to this particular case, what is the estimate? Y1 bar minus Y2 bar plus or minus Z alpha O2 square root of sigma 1 square n1 plus sigma 2 square n2. Okay. And then previous homework, extend it to construct 95%. By the way, by given, yes. Construct 95% confidence interval for mu1 minus mu2. Mu1 minus mu2, okay, not mu2 minus mu1, mu1 minus mu2. And interpret the results. Right. Now you see, in order to perform this test, you need to know sigma 1 square and sigma 2 square. Let's consider the case sigma 1 and sigma 2 square are not known. Now what we do? Now remember one sample case. Now we see earlier we were talking about one sample case. Earlier. Now we are talking about two sample case. What was our topic? Comparing two population means. But it is equivalent to what? Two sample case, isn't it? Now if you want, you can call the situation as two sample case. Why? Because we are having two samples. One sample for each population. So that if you want, you can call what we are discussing now to be two sample case. And what we discussed earlier to be one sample case. See? Right. Now, if you recall what we discussed under one sample case, we said especially small sample case, y bar minus mu naught s divided by n square root to follow what distribution? T distribution is n minus. So, and then what is the Z test? Y bar minus mu naught sigma divided by square root of n. This is having Z distribution. And this one is having T distribution. Difference is what? Here what we have is S, here what we have is sigma. So it is like what? Sigma is replaced by S, the distribution is T. But unfortunately, or otherwise fortunately, in the two sample case, when we replace sigma by S, we do not find the corresponding distribution to be T. We do not find the distribution to be T. That is the challenge. Now, what is the statistic we're talking about? Z is equal y1 bar, y2 bar, mu1, mu2, sigma 1 square n1, sigma 2 square n2. This is what distribution? Z distribution. But if you replace this by y1 bar, y2 bar, mu1 minus mu2, s1 square n1 plus s2 square n2 does not follow. Okay, does not follow the T distribution. This is the problem. Tables I cannot share again. You find it from a person who was around. Can we compare these two samples doing separate reset tests for two samples? What do you mean by that? No, our interest is comparing the two means. So how can we perform separate set tests? You mean, are you talking about? Go on, wait. By the way, now you see this compare. Can we compare these two samples? Hope everybody can see what I did on the screen, my highlight. Thank you, whoever did the communication. Okay, this is good. Now you see, compare these two samples. Do we ever have the interest of comparing samples? No, we are not interested in samples. Why? No point comparing samples. The reason is that if you take another sample, you will find values to be different. Did you get the point? Of course, we will have only one sample from each population. That is true. But the thing is that our interest is not to compare the samples or the sample means. This is very, very important in the sense that I find lot of students, let me use the word students, okay, when specifying the null hypothesis and alternate hypothesis, going by sample means. We are never interested in sample means. We want to know what is happening in the population. Because only the population mean is a constant. What is the point of talking about value of a variable? Observation to observation values are different. So what is the point of talking about one value? One such value? Hope everybody is getting the point. Our interest is what? The population values, parameters. So keep that in mind. We formulate the null hypothesis and alternative hypothesis using parameters, mu, sigma square, likewise, not using y bar. Keep that in mind. You will not have marks if you go by y bar. Okay. Now we see null hypothesis H naught, mu1 is equal to mu2. Okay. Not y1 bar is equal to y2 bar. Okay. Wrong. This is wrong. We are not interested in that. This is what we are interested in. Whether the two population means are same. Population means are same. Sample, who is interested in sample? If you take one more sample, you find values to be different. What we are interested in is population values, parameters. Okay, population summations. Right. That was interesting. Thanks to, well, whoever our colleague. Okay, right. So now the challenge is that this does not have the t distribution. Thing is, people have found if sigma 1 square is equal to sigma 2 square, then an exact distribution exists. If sigma 1 square is equal to sigma 2 square, regardless of the values, 50 and 50, 100 and 100, 65 and 65, 35 and 35, or 21 and 21, likewise. If the two variances are, population variances are same, then we find an exact distribution. Yeah. So, when the population variance are not known, what we do is that we replace population values by sample values. But in this particular case, unfortunately, if you replace them directly, you find that you don't find a corresponding distribution to be t. That is a challenge. But people have found in the absence of these population variances, in case if the two population variances are same, don't worry about values. Values are not known. But if the two population variances are known, not the known, if the population variances are same, we don't need to know the value, but if the two values are same, then an exact distribution exists. Okay. So one might ask the question, if we don't know the values, how do you know whether the two values are same or not? Isn't it? Which is fair enough. But the thing is that without knowing the exact value, maybe in the literature, you might find that people have understood variability to be same. Variability to be same means that the variances are same, but we have no idea about the value. So from the literature, you might find sometime information about whether the two population variances are same or not, but not the values. We are not interested in value. In fact, values are not required. All what we want to know is that whether the population variances are same or not. Okay. If we happen to have the two population variants to be same, then an exact distribution exists for this particular case. This particular case is that well, we are talking about something equivalent to this statistic, then we find an exact distribution exists. Let's discuss so that you understand that quickly. Right. Now we are talking about is sigma 1 square is equal to sigma 2 square. Sigma 1 square is equal to sigma 2 square, and that do we have two values? No, we have only one value because first one is equal to second one. So it's like we have only one sigma square now. We have only one value. Both are same, and then we have only one value. Interestingly, okay, right. So if that is the case, then above situation, then y1 bar minus y2 bar, mu1 minus mu2 divided by sigma square n1 plus sigma square n2 square root. Isn't it? Which is equal to, now left hand side we have z is equal now y1 bar y2 bar minus mu1 minus mu2 divided by sigma square root of 1 over n1 plus 1 over n2. Isn't it? You what we have. Because sigma square is common, you take it out and take it out of the square root sign also. So we have sigma times one over n1 plus 1 over n2. Right. See, now we have only one sigma. So that in the absence of sigma, what do we need? We need to replace this by estimate. We need to replace this by estimate. Now the question is, what is the estimate? Earlier, remember what we said is estimate of sigma is S, sample standard deviation. But now, thing is that we have two samples. So from the two samples, we have two sample standard deviations. So that the first sample standard deviation is also an estimate of sigma. Second sample standard deviation is also an estimate of sigma. Okay. So what now? We have two estimates for the same parameter. You understand? Now we have two estimates for the same parameter. How do you handle this kind of situation? You can't just ignore one value and then go by the other value, larger value. Why not? Why only larger value? Why not the smaller value? If you take smaller value, why only smaller value? Why not the larger value? So those are the questions. So obviously we need to use both. Usually, what is the usual approach? We take the average, isn't it? We take the average. Usual approach is that then. Thus, estimate of sigma hat indicate what? Estimate of sigma. Okay. It's usually taken as what? Sorry, sigma square. S1 square and S2 square divided by 2. But the thing is, so in this case, this is equal to what? S1 square multiplied by half plus S2 square multiplied by half, isn't it? Means equal weights. Weightage is same. we give equal weightage to both values. Sometimes we find it is not fair. Why? It's possible S1 is based on N1 is equal 30. S2 square is N2 based on 12. Is it fair to take the simple average? Or is it fair to give the equal weightage? No, it's not fair. Why? If a value is coming from a larger sample, it's more reliable. Isn't it? If a value is coming, if an estimate is coming from a larger sample, it's more reliable compared to an estimate coming from a smaller sample. So that most reasonable thing is that we give higher weightage to the estimate coming from a large sample and then give less weightage to or smaller weightage to the estimate coming from a smaller sample. Isn't it? That is the most reliable thing to do. Now see, calculating GPA. Calculating GPA. Suppose everybody knows that GPA is what? Summation CIGI divided by summation CI. Isn't it? You have weighted it to credit size. Weighted to credit size. Let's say 2 subjects. Subject 1, subject 2. And then 2 students. Student 1, student 2. Subject 1, 2 credit. Subject 2, 3 credit. Now, this student has got an A for this course, and then B for this course. Second student, student 2, is having B for the first course and then A for the second course. If you take the simple average, A and B, both students are same. If you take the simple average, GPA, grade point is 4, grade point is 3, grade point is 3, grade point is 4. So the average is what? 3.5, 3.5. So that both are same. But the thing is, first student has got an A for the 2 credit course and then B for the 3 credit course. Whereas the second student has got B for 2 credit course and then A for 3 credit course. Courses are of different sizes. One is 2 credit, the other one is 3 credit. So that now who is the better student? Well, if the content is small, I suppose it is easier to get a better grade compared to if the content is large. Yeah, you have a lot to study. Okay. A lot to study. Thinking effort is same. The thing is that more areas or the content is higher. So that if you take that into account, then you find second student to be better than the first student. This student is better than this student. Because second student has got an A for the 3 credit course and then B for the 2 credit course, whereas second student has got an A for the 2 credit course and then B for 3 credit course. Because of that, second student is better than the first student. So that if you calculate the GPA, GPA of student 1, GPA of student 1 is Student 1, 2 times 4 plus 3 times 3 divided by 5. GPA of student 2, 3 times 3, student 2, 3 times 3 plus second, sorry. We are talking about now this. Okay. B grade for B grade for 2 credit course, and then A grade credit size is 3, and then the grade is GI is 4 divided by 5. So here we have 8, 9, 17 divided by 5. Here we have 18 divided by 5. This is 3.4. This is 3.6. So now you can see second student is better than student 2 is better than student 1. Now see, this is what is called weighted average. GPA is weighted average. Okay, right. Now, estimating the population variance also, we need to take the weighted average. By the way, time is just 2 past 10 o'clock. I think time to have a break, isn't it? Let's have a break and start. Well, time is up. Shall we start? Hope everybody's ready. Now, if you can recall what we discussed at last is to be exact, weighted average. And then the reason behind that was what we are aiming at is now an estimate of sigma square. Now we have only one variance. Thing is that we have two estimates now, S1 square and S2 square. So, oh, just a minute. Average means what? Correction, average is divided by 2. Can everybody get that corrected? So, usually what we do is we simply take the average. S1 square divided by S2 square divided by 2. But the thing is that if you are taking the average, then you see we are giving equal weightage, half and then half. Okay. But sometimes we find samples to be of this form so that allocating equal weightage is not reasonable. We know estimate coming from a larger sample is more reliable, so that we should give higher weightage to the estimate coming from a larger sample and then less weightage to the estimate coming from a small sample. So to take that into account, we can calculate the weighted average. I think I need to get back to the screen. Right. So instead of having estimate to be sigma square, estimate to be of the form S1 square 2, we'll have the estimate weighted to the what? Now, weighted to the sample size. To be exact, weighted to the degrees of freedom. So that N1 minus 1 S1 square plus N2 minus 1 S2 square divided by N1 minus 1 plus N2 minus 1. This is like, remember, the credit size 2 plus 3, we had 5, likewise. And then this is to summation Ci, Gi. So this is like C1, C2, this is like G1 and G2, and summation plus. Okay, and summation Ci is this and this C1 and C2. Got it? So, by replacing, now recall what we had. We said was y1 bar, y2 bar, mu1, mu2 divided by sigma square root of 1 over n1 and 1 over n2 is what we had. Now replacing sigma by this estimate. This is, by the way, sigma square. Okay. So that what we have is then y1 bar, y2 bar, mu1, mu2 divided by n1 minus 1 s1 square plus n2 minus 1 s2 square divided by n1 plus n, sorry, that's right. Okay, let's make it like n1 minus 1 plus n2 minus 1. That is this part, isn't it? that is this part, and then 1 over n1 plus 1 over n2, whole thing square root. Okay. And this has, I said, exact distribution T n1 plus n2 minus 2. Why? Because it is n1 minus 1 plus n2 minus 1, which is n1 plus n2 minus 2. Because of that, this is called T statistic, since this statistic is having T distribution. This is called T statistic. But remember, now this T statistic based on 2 samples, so that we can call this to be 2 sample T statistic. 2 sample T statistic. And accordingly, the test is called 2 sample T test with specific condition satisfaction. By satisfying a specific condition. Then, what is that specific condition? 2 population variances are same. Because of that, we call this statistic to be, this test to be pooled t-test. Why pooled t-test? Pooling. Pooling means combining. So we pool, combining. So this time we obtain the estimate of the variance by pooling or by combining information coming from both samples. Because of that, this test is called pool t-test. So in order to perform pool t-test assumptions, pool t-test, independent sample, and then sigma 1 square is equal to sigma 2 square. Then data follow the normal distribution. Okay. So in case, okay, so these are the assumptions. In case if sigma 1 square is not equal to sigma 2 square, only an approximate test can be performed. So no exact test if the 2 population variances are different. Right, so this is about comparing 2 population means using specifically pool t-test. So here too, you can have one tail test as well as 2 tail tests. Interestingly, now see, critical value has to be obtained from what distribution? N1 plus N2 minus 2. Okay. And then alpha divided by 2. So this is how you need to get the critical value. If the test is 2 tail, otherwise alpha. So keep that in mind. Homework. Y1 bar is 150, y2 bar is 180, S1 square is 250, S2 square is 350, N1 is 15, N2 is 20. Test H naught, mu1 is equal to mu2 versus HA, mu1 is not equal to mu2. Alpha 0.05. 2 test H naught, mu1 is equal to mu2 versus HA, mu1 is smaller than mu2. Alpha 0.05. That's the homework. Well, just one thing you need to be careful with, or otherwise you need to keep in mind. Now we see with all these homework, I gave H naught and HA, isn't it? But real world, I am not behind. The real world case, you all are independent in the sense that you all are performing alone. Isn't it? I will always be behind you or every one of you. So that given the situation, you should be able to decide whether the test that you are going to perform is specifically, well, formulated null hypothesis and alternative hypothesis, specifically based on that, what is the consequence? Test whether the test is one tail or two tail. Okay. That is very crucial because it is possible when you perform one tail test, you can reject the null hypothesis, whereas if you perform the two tail test, you cannot reject the null hypothesis. Why? The critical value is larger in two tail test. Then remember? Right. Very crucial. Even a computer cannot decide that. This is the thing. Calculations computer can do. But what the computer cannot do is deciding whether the test is one tail or two tail. So this is very, very important. Anyway, when it comes to performing a test, we use computers. So that calculation is not that important. Even if you make a simple mistake in doing the calculation, it's not that crucial. But the thing is that you should be very smart in deciding what the computer cannot do. Okay. Certain things computers cannot do, only humans can do. See, this is where it becomes very crucial. Well, otherwise, we can use computers. Okay. Deciding whether the test is one tail or two tail. So, in fact, in the examination also, I allocate, it's like almost 50%. 50% of the mark allocated for the question with respect to deciding or correctly deciding the test is one tail or two tail. How do you decide that? I have given several examples, but when it comes to an examination, now real world situation, you think of the possibilities. Accordingly, you can decide. Now remember, I told you that now two sample case, two varieties. You have no idea how the important one is going to perform under our conditions. So it may be higher or otherwise less. Okay. But if the question is like improved diet and the normal diet, obviously what is expected is performance from the improved diet to be better. Isn't it? So in that case, one-tail test. Okay. Likewise, maybe when it comes to examination, by looking at the story given in the question, you should be able to decide. For instance, if the question says is just to compare, obviously no information is given the possibility of one to be better than the other. Then it has to be two-tailed, just to compare. But if the objective is to test whether one is better or is worse than the other, then naturally the test that you need to perform is one-tailed test. So keep that in mind. As the way the question, as the way it is worded, as the way the words are given in the question, you should be able to decide. Under real world situation, you should be able to assess the situation and then decide. Okay. Well, two diets. One is with the vitamin supplement, the other one is without that supplement. Now, what do you expect? See, now we know, everybody knows the impact of vitamin, isn't it? So, with vitamin, better, isn't it? Maybe higher weight gain or the better performance, likewise. So, then it has to be one day. Okay, so that's very important. Now, I have said this, keep that in mind when it comes to an examination. Right, so it's about comparing the two population means by performing the test, specifically Pulte test. Well, here too, we can construct the confidence interval. So the confidence interval for mu1 minus mu2 is given by y1 bar minus y2 bar plus or minus t n1 plus n2 minus 2 alpha divided by 2, and then n1 minus 1 s1 square plus n2 minus 1 s2 square divided by n1 plus n2 minus 2, and then 1 over n1, 1 over n2. This is how the confidence interval is given. Okay. All right. Now, as usual, homework is getting extended. Third question, construct 95% confidence interval for mu1 minus mu2 and interpret the results. Okay. But with that, let's conclude comparing two population means under two independent samples. Now, two independent samples. Remember that. What do you mean by that? We go from first population, you took a sample, second population, you took a sample. So that the two samples are independent. But sometimes we have the data of the form from each unit. We record two values. Under condition 1, one value, and then condition 2, the other value. Example, let's say course assessment before the course, after the course. Isn't it? From each student, we have before the course value and then after the course value. Isn't it? And then say 25, maybe 53. Likewise, we have values. Sometimes we have this kind of situation. And then maybe assessing a new diet on weight gain of pigs. Weight gain of pigs. Okay. Before introducing that diet, and then after having that diet for 1 month or the 2 months, weight gain. So for each animal, we have two values. Or otherwise, sometimes we assess two drugs on the same patient. Two drugs on the same patient. Huh? Oh, everybody got it clearly. Two drugs on the same patient. How come is that? So one might think of like, after giving the first drug, a person will be free from the disease. So by the time we introduce the second one, we are introducing it to a healthy person. Isn't it? If that is the case, it's very funny, isn't it? Is it an experiment? No. Then it is not a study. Any comparison has to be a fair comparison. So that when we introduce a drug, second drug also, the condition of the patient has to be exactly the same. Then one might be thinking of, we are talking about the situation where the effect of the first drug is nil, or there is no impact of the first drug. No, there is nothing like that. We have sometimes diseases for which we cannot have the complete cure, isn't it? All what we do is we just manage. For such situation, now we can understand, we can assess, let's say, both drugs on the same patient. First drug in first spell, and then second drug in the second spell. Isn't it? Okay, because all what we do is we just manage. So not for every diseases. Okay, now like before the course and after the course. Before introducing the diet, after introducing the diet. And then under first drug, under the second drug. But in each of those, situation is such that from each unit we have recorded 2. When we record 2 values from each unit, can we expect both values to be independent, or the 2 values to be independent? 2 values coming from each unit to be independent? No, isn't it? Because it is from the same unit. But look at these values. Look at these values. Now, left-hand side. What is the smallest value? 25. This side. What is the smallest value? 53. Right. And then what is the largest value on this side? 80. What is the largest value on the second set? 95. And now you can see small is corresponding to small and the large is corresponding to large. Isn't it? Well, that's natural. Do you expect, the person with lowest value before the course to be the expect, not impossible. understanding clearly, do we expect this person to be the best person at the end? No, usually not. With everybody, we expect an improvement. With everybody, we expect an improvement. Not that improvement is a constant. Oh, that can vary. That can vary. I mean, like see, we are talking about talking about one time when you toss the coin for 50 times, you get 22 heads, but second time you can get 28 heads. What is the reason? Don't know. So likewise, you can see that even if they study more or less the same amount, and then even if you think of the uniform set of students, you find this difference to be before and after difference to be different. You don't find with every student value to be exactly the same. But in general, what we can expect is that if the initial value is small, n value is also small, relatively. Okay? If the initial value is small, n value is also small. If the initial value is large, n value is also large. What do we mean by that? From one value, you can predict the other value. From the initial value, you can predict the n value. If you can predict, are they independent? How can they be independent? If they're independent, you can't predict. Is that clear? This is what is meant by when we have two values from the same unit, you can't expect them to be independent. But one big assumption in statistics is that the values have to be independent. So how do you correct then these values, dependent values? The simplest is that you take the difference. You take the difference. Let's say after minus before. Or otherwise before minus after. It doesn't matter. You just take the difference. By taking the difference, you are converting two values into one value. Two sets into one set. Now, from first value, can we predict the second value? No, it is not possible. Because first difference is from the first person, second difference from another person. So this set is independent. This set is independent. Interestingly, now we have only one set. It's like what? We have converted two samples into one sample. It is like we have converted two sample situation into one sample situation. So that now we can deal as the way we dealt with one sample case. Isn't it? That's the principle. Right. So the situation is that from every unit, we have recorded two values. So that we can call the situation to be what? Observations are paired. Observations are paired. So we're talking about earlier, we're talking about two independent samples. This time, samples are not independent. We have a situation of paired observations. Okay. So this is how you deal with paired observations. By taking the difference, you get rid of that dependence. H naught. Still, we are talking about two groups, before and after. Before and after. So that still we can go by like mu1 is equal to mu2, or otherwise mu1 minus mu2 is equal to 0. HA, mu1 is not equal to mu2, or otherwise mu1 minus mu2 is not equal to 0. So that same as two independent samples. Formulation of hypothesis and null hypothesis, alternate hypothesis, exactly the same. But if mu1 is equal to mu2, what can you say about mean of these differences? Mean of this difference is equal to mu1 minus mu2. So this time, if you want, we can formulate the null hypothesis in one other form, mu d is equal to 0. Because now we can talk about mean of differences. Earlier it was not possible. Why? Because we did not have well the two values or the two values under two situations from the same person. We did not have in that form. So that we could not work out individual differences. So that mu d was not possible. But this time, mu d is like theoretically it's a possible form. So here then mu d is not equal to 0. What is the estimate of mu d? Is the sample of mean of these differences. Now we have taken the difference, isn't it? We have differences. How many differences? Equal to number of units. 1, 2, 3, going up to let's say 10. So based on this 10, we have d bar. Isn't it? Estimate of mu d is d bar. Okay, once you have differences, you can have d bar. So that. Now we can think of performing the test. Now it's like ultimately one sample case. So that the t statistic is what? Estimate minus null hypothesis divided by standard of estimate. What is the estimate? D bar minus mu d divided by standard of now if mu d is equal to 0, this becomes according to this becomes 0. So that you can have just d bar divided by standard of d bar. And this is having t distribution with n minus 1 degrees of freedom. And as usual, if t in terms of absolute value is greater than nt n minus 1 alpha divided by 2, reject h naught and do not otherwise. This is two tail, and if it is one tail, this becomes alpha. Exactly, it's very straightforward. Homework. Maybe we continue before the course, after the course. Candidate, student. One, two, three, four, five, 6, 7, 8, 9, 10, 30, 42, 70, 92, 60, 85, 4, 55, 5, 60, 80, 25, 60, 7, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, 121, 122, 1 43, 55, 53, 85, 83, 80, 96. Right. Test H node. Mu after is greater than mu before. Thus, sorry. Versus mu after versus HA mu after is greater than mu before. Right. Now you see, if the observations are paired, this is how we handle the case. So ultimately what we did was, we perform one sample t-test. But to begin with, the situation we had was paired observations. Because of that, the test is called paired t-test. The test is called paired test. So if the observations are paired, the test that we perform is paired t-test. But otherwise, we perform two independent sample t-tests. Right. But it's possible. If we want, we can have the data in both forms. We can have the data in both forms. Now you see, in all three examples, we discuss. Now see, before the course and after the course. If we want, we can have one set of students without going through the course assessment. And then another set of students, who have gone through the course. Okay. By the way, hope you noticed that this time we find after value to be smaller. So once in a way, but that is possible. Now imagine there is no impact of the course. There is no impact of the course. If that is the case, then you expect the values to be more or less same. But this case, as the way you find values, it's like course is very effective. More or less everybody is having an improvement. But once in a way, you can have, now this value is smaller. This value is also smaller. Okay. Got it? So you are taking the difference. You find -2. Here also -2. So keep that in mind. Right. See, we want, you can have two separate samples, so otherwise we can have the same group studied under both situations. And remember those two drugs. There you were talking about condition of the patient is exactly the same. But if the condition varies, condition changes, then we cannot have this approach. Okay, cannot have this approach. So that For every disease, we cannot think of, but diseases such as, diabetics, asthma. So that kind of cases, we can use this approach because there is no permanent cure, isn't it? All what we do is we just manage. Such a case, we can use same patient. Otherwise, we have to use two different groups. Okay. Right. Now, say for diabetics also, if you want, you can use two different groups. Otherwise, we can use the same group. Now we have a choice. Then the question is that what is better? Isn't it? Then the choice is what is better. We go through this example. Now you see, in terms of differences, we have 38, 25, 53, 28, 80, 95, 15. 95. This is how we have the values. Now, if we assess the variability of the three groups, variance of the first sample, variance is difficult to calculate, but let's calculate range. Range is how much? 25 to 80 at 55. Sorry, 25 to 80 is 55. This time range is 53 to 95. That's 47. 55, 95, that's 42. Here, range is equal 15 to 38. 23. 15 to 38. 15, 30 plus 8, 23. Right. What can we say? Variance is smaller for the differences compared to individual values. Variance of the differences is always smaller. So if the variance is smaller, leads to standard error of the estimate. Standard error of the estimate is smaller. If the standard error is small, t-values will be large, meaning there's a higher chance of rejecting H0. More precise estimates, standard error is low. Those standard error. Okay. So now we can understand standard error in the paired t-test is smaller than the standard error of two independent sample case. Numerator is same. Mu1 minus mu2, y1 bar minus y2 bar is same as d bar. Numerator is same. Only the denominator is different. Standard error part is different. Variance of the difference is smaller. So that we can see. Now, if we have a choice, now we find that paired t-test is better because standard error of the estimate is smaller. Right. One can question, how come we get the standard errors to be smaller or the variance to be less? Now, the reason is first person, say in this case, 40 and 78, second one 25 to 53, likewise. Now, within the first group, I can see there's a big difference between individuals. Whatever said and done, individual effect is also there, isn't it? Individual effect is also there. But in the case of paired observation, by taking the difference, since it is the same person we have on both sides, by taking the difference, we remove that individual effect. So that ultimately individual variable is removed by taking the difference. And thereby you find, since part of the variable is removed, you find less variability with differences. Thereby we have more precise estimates. Okay, so this is the reason behind more precise estimate. Now you see, sometimes we have a choice, isn't it? Sometimes we have a choice, like in the case of two drugs. Sometimes it is possible we can have both approaches. So in such a case, question is that which one is better? Now you understand paired observation case is better than the two independent samples. Now you see, is that interesting? We found paired observation to be a problem to begin with. Why? We said that there's an issue of values are not independent. So we started with like we are having a problem. But ultimately it turned out to be what? Better. Having that problem was better. So that when you have a problem, don't get disappointed. You see how you can relate statistics to real world, isn't it? So just because you have a problem, don't get disappointed. You might find that you will be better off. Isn't it interesting? We started with saying that we have a challenge. Right. So that's how you handle the case. So as far as possible, it's good to have the observations of the form. Yeah. Sometimes you find that when you plan it in such a way we can have observation to be impaired. Thinking of two situations. Maybe you plan it in such a way from each person you can have the data for both conditions. Right. Well, shortcut method of calculating standard error of the differences. I see here, in order to perform the test, standard error of the difference. Standard error of the difference can be calculated using simplified formula summation di square, summation di whole thing square divided by n, and then n times n minus 1 square root. Right. That's about paired t-test. Now recall something we discussed with the previous situation is two independent samples. By the way, here also you can construct confidence intervals for mu d is what? D bar plus or minus t minus 1 alpha divided by 2 times what? Standard error of d bar. Okay. Yeah. Right. Now recall the previous one, whole t-test, because that is the exact test. Other one is only an approximate test. We did not discuss the approximate test in our calculated test statistic. You don't find that much of a difference. So actually the only issue is getting the critical value. Critical value is related to the degrees of freedom. So that is the only difference. So that's why we didn't discuss that much. Okay. So, but somehow, see, one big assumption that we need to fulfill if you will perform whole t-test, or first of all, we need to know whether we can perform whole t-test or not. Okay. The test that we can perform is whole t-test or the approximate test. You will perform the pool t-test to make sure that two population variances are same. Remember that time what I said is, how do you know whether the two population variances are same or not? You don't need to know the value. I said is that all what we have to make sure is that two values are same. How do you know? One method I said is that from the literature. Suppose it's difficult to find such information. In such a case, actually, we can perform a test to determine whether the two population variances are same or not. Testing homogeneity of two variances. So naturally, what is H naught? Sigma 1 square is equal to sigma 2 square. And then HA is opposite of this. So I said null hypothesis sigma 1 square is equal to sigma 2 square. Otherwise, sigma square divided by sigma 2 square. If the two are same, the ratio is 1. And then alternative is what? Alternative is then sigma 1 square divided by sigma 2 square is greater than 1. Is greater than. Okay. Now the question is, see, compared to the way we discuss this for the previous test. See, he said test, T test, chi-square test also. See, we had it of the form, comparing two groups, let's say. Yeah, forget about one sample case, let's say two sample case. We had it of the form mu1 is equal mu2, and then mu1 is not equal to mu2. Yeah, let's say two sample case, not equal. So that we had it to be, even if it is one tail, we had it of the form difference. We had it of the form difference. See, that time we had mu1 is equal to mu2, or otherwise mu1 minus mu2 is equal to 0. That time we didn't take it as mu1 divided by mu2, isn't it? So now the question is, why are we having it in this form? Why not sigma 1 square minus sigma 2 square is equal to 0? Okay. Right. The reason is that now we can understand all the tests that we discussed so far. See, we had our estimates to follow a specific distribution. Whenever we want to perform a test, we need to know the distribution of the statistic or the estimate. Distribution of the statistic or the estimate. Okay. Right. Now, what are the estimates of population variances? S1 square and S2 square. So one possible estimate is S1 square minus S2 square. Other possibility is S1 square divided by S2 square. Those are the two possibilities. Right. I think now you can understand reason to formulate the null hypothesis and alternative hypothesis of the form ratio is that S1 square divided by S2 square, for the ratio of two variances, follows a distribution called F distribution with N1 minus 1 and N2 minus 1. 2 degrees of freedom. F distribution, which is a 2-parameter distribution, where the two parameters are degrees of freedom of the first sample and degrees of freedom of the second sample. But S1 square minus S2 square, the distribution, don't know. We haven't found any distribution for the differences. That is the reason we formulate null and alternative of the form ratio. Okay, right. And then see, straight away I have formulated the alternativity of the form greater than. Well, the reason behind that is, then one can question, can't we perform two-tailed test? Right. First of all, F distribution is also of the form like this. Also of this form. Skewed. Sorry. Skewed. 0 to infinity. Okay. So pretty similar to the chi-square distribution. Compared to T distribution and Z distribution, well, this is skewed. This is positively skewed. Positively skewed. Right. So that by having the right tail critical value, you cannot directly work out the left tail critical value. Of course, relationship is there, but it's not straightforward, isn't it? Why? It's not symmetric. And then, well, starting point is 0. And then, when taking the ratio, which one we are going to consider into the numerator, and then which one we are going to consider into the denominator is up to us, isn't it? S1 square divided by S2 square. What is S1 square? Who gave the label 1? It's a researcher. It's up to us. It's up to us. So then, we have a choice. We have a choice of having which one to be considered as S1 square and which one to be considered as S2 square. So that when calculating the statistic, I said S1 square divided by S2 square. So since it is having the F distribution, we call S1 square divided by S2 square to be F statistic. When we are calculating F statistic, we always take higher value on top. We always take the higher value on top. So that this F value is always greater than or equal to 1. F value is always greater than or equal to 1. Okay. Because of that, since higher value on top, what is the possibility? Either the numerator variance is sigma 1 square is greater than sigma 2 square, or otherwise sigma 1 square is equal to sigma 2 square, isn't it? Because minimum value possible is 1. Minimum value possible 1 in sense that it is equal. So the possibility is then null hypothesis is equal, alternative is sigma 1 square is greater than sigma 2 square. So that we can always perform the right tail test. One tail test, the right tail. Because of this convenience, usually in the F table, you find only the right tail values. Only the right tail values. Okay. Let me now share a copy of that F table. Oops. Yeah, take always alpha as 0.05. If alpha is not given. Okay. right? You can see shape is pretty similar to chi-square distribution. And then the table entries are again same as in the chi-square distribution. Same as in the chi-square distribution. But what you read are the critical values corresponding to this time only 0.05. This whole table is for alpha 0.05. From this table, you cannot read the critical values corresponding to different alpha. Okay. Right. Now, in order to read the value, see this is NDF, numerator degrees of freedom, and then DDF, denominator degrees of freedom. Now, remember S1 square divided by S2 square. So that S1 square, variance, which is the larger one, and degrees of freedom of that one is what is called numerator degrees of freedom. And then the degrees of freedom of the degree of freedom of S2 square is considered from DDF. First, you identify the degrees of freedom. Suppose it is like 10 and then 20, then the critical value is the value at the intersecting point of 10 and 20, which is 2.35. Okay. So as an example, F 10, 15, 0.05 is, how much was that? 10 and 15 is 2.54. 2.51. Therefore, rejection rule, if F is greater than F numerator degrees of freedom, denominator degrees of freedom, alpha, reject H naught, do not otherwise. So that in case if you want to know whether the two population variances are same or not, you can perform an F test. Using an F test, you can determine whether the two variances are same or not. You reject the null hypothesis, meaning population variances are different. Otherwise, we do not reject the null hypothesis, population variances are not different. So that in order to decide what two sample t-test that you want to perform, first you can perform this F test and then decide whether the two population variances are same or not. If the population variances are same, then you can perform the pool t-test, and if the population variances are different, then you can perform the approximate test. So homework Now remember we had several examples for two sample t-test. Two sample t-test. So perform the f-test. F-test based on last two sample t-test example. Not example, exercise. Two sample t-test homework. Alpha 0.05. Right, so that's about testing homogeneity of variance. Okay, I think with that we can conclude comparing two parameters altogether. First, we went through comparing to population means, and then we went through comparing to population variances. Okay. When it comes to comparing to population means, we perform what? Two sample t-tests, or otherwise it's possible paired t-test. Two sample t-test, otherwise paired t. Two sample t-test is of two forms. One is the pool t-test, the other one is the approximate test. Okay. When it comes to comparing to population variances, then need arises when the two samples are independent. Okay. F-test is possible if the two samples are independent only. Okay. But need actually does not arise when observations are paired. Why? Because you are converting ultimately into one sample. So we are talking about one variance. No two variances are there. Okay. Right. So with that, we can conclude comparison of two parameters. Next. Well, think of a case. Comparing maybe let me get back to the screen again. Right. Right. Let's say we have an objective of comparing two diets with two different calorie contents. One with low calorie, other one is high calorie. Two diet with two different calorie contents. What do you think? What the outcome is? Suppose comparison is weight gain. what do you expect the outcome to be? I suppose, everybody knows that already, or otherwise it is well established. With higher calorie content, you will find the weight gain also to be higher. Yeah. Well, there's nothing to study. It's well established. With high calorie and low calorie, with high calorie, body weight gain is higher. With low calorie, body weight gain is less. That's how we have. Very straightforward. But the thing is, how the weight increases against the calorie content. See, weight gain. Is it according to something like this? Or otherwise, according to something like this? Or otherwise, according to something like this? Or otherwise, it is according to something like this? It's not very clear, is it? Whether the pattern is well in this form, or this form, or this form, or this form, likewise, so we can think of like different forms. All forms describe what? When calorie content increases, body weight or the weight gain is also increasing. Although it is well established that when the calorie content increases, the weight gain increases, or we will have a higher weight gain. How the weight increases with the increase of calorie content is not very clear. So we could be interested in what? Studying this pattern. Studying this pattern. What do you mean by studying this pattern? Studying the relationship. Study the relationship. So interest is what? Not to study the different. Different is well established. But we are interested in something more than that. How the change takes place. Okay, studying the relationship. So let's have the topic. Studying the relationship. Consideration is that relationship between two variables. Of course, can we study a relationship with one variable? No, you cannot. Relationship between only two variables, okay, not more than two variables, at least to start with. Relationship between two variables. Let's say two variables are denoted by x and y. X and y are continuous. X and y are continuous. If x and y are continuous, the technique that we use to study the relationship is called regression. Technique that we use is called regression. When it comes to studying relationships, maybe before coming into regression, when it comes to studying relationship, sometimes we find you can see one variable depends only on one or several variables. Y depends only on one or several variables. Another possibility is that y depends on, well, large number of variables. Large number of variables, but some are more important. Some are more important. If only depends only on few variables in that they depend only on keyword, only on few variables. Approach is called deterministic. And then if large number of variables are there, can we ever study all those variables and then find the relationship? It's not possible. And then, as I said, that certain variables are more important when it comes to dependency of y. So that we could be interested in studying relationship between response, well, this y variable, and then we are talking about relationship, y variable and those important variables. So since the relationship out of large number of variables, now we are considering only few variables or there are several variables. So that an exact relationship cannot expected. An exact relationship cannot be expected. So in such a situation, the approach is stochastic. In the sense that stochastic or otherwise probabilistic. Okay. Very often in biology or otherwise in natural science, we find relationship to be of this form. But sometimes in physical science, we find them to be of this form. I suppose you can remember in physics, we talked about, let's say, rate of heat loss, theta, otherwise Q divided by T is equal to Ka, blah, blah, blah. Remember? Okay. So, see, we are talking about an exact relationship. So, such are called deterministic. But every time you cannot have that kind of relationship. Okay. Now, maybe as an example, protein content and then weight gain. Fixed them, well, 5%. 10, 15, 20, likewise 25, 30, likewise it's 5%. Suppose with maybe with a person, you found it to be this much. So another person, more or less same, not the same person, more or less the same. Imagine we gave same 5% diet, 5% protein content diet. Do you think that person will also have exactly the same weight gain? No. So that will be different. And then 10%, you might find it to be, say, Something like this, isn't it? Like that. Okay. So ultimately, we have set like this. See, this time we don't find all the points to be on an exact curve. You don't find all the points to be an exact curve. But if you study something like minutes and hours, 1, 2, 3, then you can see, suppose 10 students study, you find all the points to be on an exact curve every time. This is what is called exact relationship. This is where we are focusing on deterministic type. But in a case like this, you see, you cannot have this kind of situation. Then points to be lying on an exact curve, not necessarily on a straight line, whatever. But we don't find points to be on exact curve. Okay. So none exact. So approach of studying, again, if I ask, looking at these points, is there a relationship between the two variables? I suppose everybody will say, yes, there is a relationship. Because these points indicate that when protein content increases, the weight gain is also higher. Okay. But the thing is that relationship is not exact. This is where we need to use what? Stochastic or otherwise probabilistic approach. This is what we discuss in statistics. And this is the technique called regression. Okay. So our focus is stochastic approach, and that is what is called regression. Okay, so that is what we are discussing. So now you can see starting point of studying relationship is what? This plot. This is called scatter plot. Starting point is scatter plot. From this only you can have an idea about, first of all, whether there is a relationship, and then what kind of a relationship is there. Now think of something like this. How about, does it indicate any relationship? No, it doesn't. This, how about this? Yes. Why? It's like underlining this kind of a line is there, isn't it? Underline this kind of a line is there. But here, if you think of such a line, you find that line is parallel to x-axis, meaning what? No relationship. Okay, so the starting point is the scatter plot. Of course, this is possible in sense that not that easy if we have more than two variables. So this course, our focus is what? Studying relationship between only two variables. Relationship between x and y, and the relationship is linear. That's straight line relationship. That is our focus. We know mathematically linear relationship is described by an equation of the form y is equal mx plus c. Linear equation. When x increases, y increases continuously. Such a relationship is called linear relationship. We know that. So the technique that we call is simple linear regression. Simple linear regression. Simple is two variables, and then linear relationship. Regression is a technique. So that is what I mean by simple mean. Two linear mean relationship is linear. So if you think of now scatter plot y and then x. This is how we have. And if you think of now the underlying relationship, suppose underlying relationship is this, and we know this is of the form y is equal mx plus c. But we don't find points on the line. There's, if you think of this, what is this value? Suppose this is x is equal xi, y is equal yi. This y is x. How much is yi? Yi can be described as this value, x is equal xi, value on the curve plus this value. That value. Value on the curve is mx plus c, given by mx plus c. What are m and c? M indicates what? Slope, and then c indicates the intercept. What are m and c? Given the curve, m and c are constants, but curve to curve, m and c are different. So that this m and c are called, in fact, better term, not the constant. Constant is not universally fixed. M and c are called parameters. Isn't it? M and c are the parameters. See, in order to calculate y for any given x, all what we need are m and c. See, parameter, only two values. So those values are called parameters. By the way, if I ask, what is the purpose of studying a relationship? What is the purpose of studying a relationship? In fact, one word answer, prediction. If you know the relationship, you can predict it. Predictions are very, very important. Now you see, before having a tsunami, if we can predict, see how much of lives and properties can be saved. See the importance of prediction. Rather than you wait and see what is going to be the outcome after tsunami. Some people are dead. Some people are still alive. Lot of properties have damaged. Some properties haven't damaged. See, are we interested? No. See, if we can predict something in advance, then you can see that we'll find it like very, very useful. Predictions are very important. In order to do the prediction, we should know what? Relationship. So that's the whole purpose. Now see, if we know the relationship between weight gain, say animal production, weight gain, protein content of the diet, then we know in order to achieve certain amount of weight, not necessarily the maximum weight, because profit may not be maximum at the maximum weight. So we need to, let's say, profit maximum is at certain amount of weight. And we know in order to achieve that weight, what should be the protein content of the diet. See? If we know the relationship only, you can do this. Say, in order to do this management, you need to know the relationship. Back to now the value yi. Then can be described as, say, beta naught plus beta 1 xi plus this difference. This describes what? Value on the curve. Value on the curve. And then if we denote this as, let's say, epsilon I, then yi is epsilon I. How much is epsilon I? Don't know. Don't know. Sometimes you find the point to be above the line, sometimes you find point to be below the line. That also we cannot tell. In fact, before having the value, we have no idea. And then thing is that in reality, do we know this line to begin with? No, we don't know. Since this part, but all what we are talking about now is how much is this value. If you think of this kind of a line, because by looking at the scatter points, you can find underlying relationship with a straight line. So that we thought of this kind of a line. And now from this line, this value then this much deviated. Since we have no idea about this value, maybe above the line, maybe below the line, so we call this to be error or otherwise residual. Error or residual. Okay. Now, y is equal mx plus c. And this, what is the difference? Difference is that in this expression, we have a term called error term. But here, no such term. No other term. That is the difference between equation and this expression. An expression of this nature, an expression of this form is called a statistical model. It's called a statistical model. Now you know the difference between statistical model and an equation. A specific term is there in a statistical model, which is the error term. Okay. So what kind of expression is that? Expression is describing a value of a variable. Describing a value of a variable. Right. Now, if you think of expected value of this yi given xi. Now, remember we discussed expected values. Expected value of a constant, mean of a constant is what? Same constant. Expected value of a constant under properties. I don't know whether we discussed this one. Expected value of a constant is same constant. Because mean of a constant is same constant. So expected value of yi given xi, straight line, is what? Beta naught plus beta 1 xi. Beta 1 xi. Why? Residual, sometime above the line, sometime below the line. So that, well, if you take above the line to be plus, below the line to be minus, then mean is how much? Mean is, what is expected is that mean to be pluses and minus, you can expect that, it to be 0, mean to be 0. Okay. So that expected value of yi given xi is beta naught plus beta 1 xi, which is of the form y is equal mx plus c. So that this line we are talking about, is what? Is expected value of yi given xi. Is beta naught plus beta 1 xi. And this is the line that we are interested in. Expected value is what? Mean. Expected value is mean. So that mean of the y values. Expected value is the mean of these y values. So set of y values, mean. Set of y values, mean. Set of y values, mean. Right. So what we want is this. What we want is this. And then how do you, well, what we want is that. And how do you get that? Only possibility is that, you see now, how many parameters are there? How many parameters are there? 2 parameters are there. So that what we want are the estimates. Beta naught hat and beta 1. So that studying the relationship, ultimately, what we are studying is this, that is, underline this curve. Underline this curve. Is ultimately then studying is what? Obtaining estimates for beta naught and beta 1. So once you have the estimates for beta naught and beta 1, by replacing beta naught and beta 1, we can have, let's say, yi hat. Those are estimated values. Yi now estimated value is beta naught hat plus beta 1 hat xi. This is called prediction equation. Called prediction equation. So using the prediction equation, if we want, now we can estimate the error. Error hat is yi minus yi hat. Yi hat is coming from the prediction equation, and yi is coming from the data. So by having this difference, then we can estimate epsilon I hat. So now, with those, we can formulate assumptions used in simple linear regression. Linear relationship. And then out of x is independent and y dependent. And then errors to be distributed normally with the mean of 0 and a common variance. Common variance. Right. I think this is a good point to call it a day. Probably before we close, shall we have the quiz for the day? By the way, some of you had asked me messages regarding the yesterday's mark sheet that I shared, saying that marks are not there and all, and then I replied to all those messages saying that I will have a look at it and then let you know. If you have submitted and then I have received them, you will have marks. Otherwise, if you haven't submitted, then you cannot have marks. I will have a look at it. Okay. And then quizzes cannot be repeated, so that don't request alternatives for that. If you happen to be absent, we will have 0. Otherwise, if you are present, you will have at least 2, even if the answer is completely wrong. Right. Can everybody get ready for the quiz? Okay. You discuss. I have homework is for you to get trained. Best thing is, you discuss among yourself, otherwise if you are going to discuss them also, thing is, we will have no time. Is everybody ready now? Unable in sense that better leave. Now, thing is, I have said how many times I said that, well, we need to make sure that, our camera is working. And examination, as you know, well, I suppose everybody is familiar with this online examinations. See, some are not around. You see, they have logged in, but not around. Aziz, every time, this problem. Aziz,
Yeah.
Aziz, why are you hiding?
No, sir.
Why?
I'm using both, sir, phone and.
Really? Okay. Fine. See, this is the other issue. Manur, we
Yes,
can't
sir. Just
see
give me
you.
one minute. 1 minute, sir.
Now, who is this Chandana without number? Chandana is not around. Chandana, are you around? Right, okay. Iruni, are you around or not? 2353.
Sir, I'm using MHC Kumarasinghe.
Sorry?
For the phone.
Did you log in by
I'm
two
using,
devices?
Yes, I'm using now MSC Kumarasinghe.
No, there was name by that. What name did I say? No, there was
2353
there
MSG
was
Kumar.
one. Thing is that, well,
Yes.
see, change the login name. Use the correct name. We are going by Kumar Siri now, change it to Kumar Siri. Don't have it, what is that, hero name. And include the number. It's what is important. Okay, 2357 is registration number, and then well, not this number, then you need to have the NIC number.
Okay, sir.
Devni Ekanayaka. Not around. Devni Ekanayaka. No. Amalita, are you around? Amalita? No. Tijana, are you around?
Yes, sir.
Okay. Can't see you on the screen. Can you have the camera on? Sampath, without a number. Sampath? No. Tijana,
Yes, sir.
so have the camera on quickly. Running out of time.
Sir, I am on traveling, that's why.
No. So aren't you going to answer to the quiz?
Sir, I will, sir, but my baby is near me, that's why.
Sorry? No, you need to have the camera on.
Okay, sir.
Right. Okay, right. I think let's go ahead and see how much of time we are wasting. Okay. Um, if H naught is rejected at alpha 0.05, and we always reject H naught at alpha 0.1. Justify the answer. Don't write stories, 1 or 2 words. Now remember, we discussed about one tail and two tail also. So that I think by now you can figure out the answer. We were telling one tail is more powerful than two tail. Now if you by now you know the reason behind that. So relate that into this. So you get the answer. So so I have see now already given the answer. So quickly, because you need to now join for the other meeting also. Mahathipan, no. Pulavan,
Excuse me, sir.
yeah. Who is it?
Sir, I'm KV Appa, sir. So I suddenly experienced a network issue. Then I rejoined again. Now,
Okay, quickly.
yes.
Masangi, Masangi Moragal. Keep the camera on, Masangi. HMAKB Herat. Herat, why are you hiding? Jairuban. Okay. Keep the camera on, Jairuban.
Okay, sir.
Right. Herath is hiding again. I don't know why Herath is hiding. Ah, Herath, is something wrong over there?
No, sir, I'm left with the phone. There's some issues.
No, but whether it is phone or the computer, make sure the camera is on. How about Gunatilaka? GRSS Gunatilaka. I think you have used more than 7 minutes. Yeah, I think today's question, everybody should get 10 out of 10. Is everybody done? Looks like everybody has sent.
So can you give me 30 seconds, please?
Okay, go ahead. They're okay?
Yes, I sent it.
Okay, right. Thank you. But still sending, huh? I think for the second time also, some are sending. Yeah, looks like all over now. Okay, I'm going to close it now. Come on, come on. Is that okay? Right. So don't send them hereafter. I'm going to save it now. Right. So the question was, oops. If we reject the null hypothesis at alpha 0.05, whether we can reject the null, whether we always reject the null hypothesis at 0.1. Say it is, suppose it is one tail 0.05. So let's say C 0.05. Now critical value for 0.1. 0.1 is larger or smaller? 0.1 is larger, isn't it? So if you want to have 0.1, how do you want this area to be? Large or small? Large, isn't it? In order to make it large, this line should be shifted towards what? Towards left, isn't it? Then only we can have higher area. This is 0. So that this is the new critical area, sorry, critical value, C.1. So now we find C.1 to be smaller than C 0.05. So that if we reject the null hypothesis, since that our critical value is where? Our critical value, so our observed value, these are the critical values. Our observed value, we have rejected in sense somewhere there, isn't it? Somewhere there in sense that 0.05 rejected means this value is larger than 0.05. So it's definitely larger than C.1. So that if we reject it at 0.05, we are definitely rejecting at alpha 0.1. So that answer is yes. Reason is critical value for alpha 0.1 is smaller than that of alpha 0.05. If the critical value is smaller, if we can reject the null hypothesis with larger critical value, obviously we are rejecting it with smaller critical value. I think this time everybody gave the correct answer, so it's good. Want to see everybody is having 10 out of 10. Right, I think that's all for today. And then yesterday I informed you, next week we will not have the meeting, both on Saturday as well as on Sunday. And then we'll have, I think, altogether one more meeting, isn't it? So this is our 7th meeting, so we'll have only one more meeting and then have the examination. Okay, any questions, concerns, clarifications, comments? Attend to homework. Right. Any questions, comments, clarifications? Yes, yes. I will let you know. Yeah, you bring those tables. Yeah. Bring those table in the printed form, not on the phone. Phones are not allowed during the examination. Calculators are allowed. If you bring the calculators only, you can use. Otherwise, materials cannot be shared during the examination. But it is no, we cannot always reject X naught at 0.1. I don't know what this, yeah, if H naught is what I said is that H naught is rejected at 0.05. And then how about 0.1? So not other way around. Okay. If it is rejected at 0.05, it will always be rejected at 0.1. Because 0.1, the critical value is smaller. Cutoff mark. Who is telling about cutoff mark? Who is telling about cutoff mark? There was something. Model paper I will send next week. Somebody's talking about cutoff point. Huh? Who is talking about cutoff point?
Yes, it's me, Ahmed.
Ahmed, what should be the cutoff point?
Mm. No, I'm asking about, sir, the past 2 years, sir, to take.
Well, I think last week, maybe yesterday also, I said that that varies depending on the performance of students.
Yes.
Okay. And do you have any value in your mind, or how about
60, sir?
60?
Yes.
60 as the cutoff pass mark?
Yes.
Okay, it's good.
No, is it? That means based on last 2 years?
No, that varied, as I said, that from year to year. There's no fixed value. No, I'm asking you any possible value that I can think of. Is
I think
60 too much or too low? Common.
I think so, sir.
Huh?
I think so.
Think what? Too low or too high?
Little bit high.
High. Okay. So how about 50? Anyway, okay, right. I think, well, as I said, that we'll see how students have performed and then decide. Okay, shall we then close it for the day?
Okay, sir. Thank you.
Right. Okay. Yeah.
Thank you, sir. Have a
Yeah.
nice
Okay.
day.
You're welcome. Yeah. Okay.
Thank you, sir.
Yeah. You're welcome.
Thank you, sir.
Sir, can
Okay.
I ask?
Yeah. Okay. Go ahead.
Sir, so
Now, your connection is not very steady, so that we cannot hear you. No, difficult to hear. Or is it? Okay, well, others can leave now. Those who want,
Sir?
can leave. Otherwise, those who want to hear this question, can wait. Yeah, who is it? Quickly.
Sir, I'm Randeep Perra.
Randeep, yes. Yeah.
Yes,
Yeah, the one
sir,
who told me yesterday. Okay, yes.
yes, sir. I want to send you my registration number and all. Yesterday you informed me. I sent it by email. Is it okay, sir?
No need to send me. Today when you logged in, did you have the number?
I logged
When you
in.
logged in today,
Yeah.
did you use that number?
No, sir. My name was there appearing in the.
No, I
Zoom.
always tell that, along with the name, to include the number, either the NIC number or otherwise registration number.
Okay, sir.
No, otherwise that's why, sometime, yesterday also with the most lot of messages, saying that the marks are not identified, although attended to quizzes, sometimes the problem is that, number is not there, and then joining by different names, so that, finding that difficult to identify marks or assign marks to the relevant name. Okay.
Okay, sir.
Anything
Okay,
else?
sir.
Somebody
Okay, sir.
was
Thank you.
another.
Excuse me, sir.
Yeah,
Sir, can
yeah.
sir, for the exam, we only need T tables and Z table.
Now, how many
Or-
tables will we discuss?
4 tables.
4 tables.
Choice.
Bring all 4.
Sir, only 2 table. I mean, T table and Z tables are only shared. I think F table and square tables are not on the chat box previously.
No, I did that. Okay. Any other questions? Yes, Hasna. No.
Yeah, sir. Can you please upload the tables in that drive folder, so certain things we can check whether we miss anything.
I have already done that, so, well, if you were not present in the meeting, of course, you cannot have it. Yes.
No, sir, sometime disconnected, so sometimes that's unable to get.
Yeah, contact a person, who was present in the meeting.
Okay, sir.
Do you know anybody? Do you know anybody else in the meeting? I suppose we have some friends, don't you? Right. Is that all?
Yes, sir. So can I ask a question?
Is anybody? Pawan, are you asking
Yes, sir.
question?
Yes, sir.
Okay. Can't
yeah.
hear. Speak a bit louder.
How is it now, sir?
Still a bit low. Quickly.
Sir,
Yeah.
earlier you mentioned so the computers cannot compute it like null and alternative hypothesis like
No.
computer application. So what if we can use machine learning algorithms to predict that based on
Yes. Well, we talk about this machine thing, during this session, because now we are talking about study relationship. Now, machine learning, in fact, the objective is just to do the prediction. Just to do the prediction thing is that with machine learning, we would not know the exact relationship. That is the issue. Okay, but you can do predictions, especially by doing it with large number of observations, so that we might find accuracy to be higher.
Yeah.
Because when we undertake a study, cannot have millions of million values, so but with machine learning, advantage is that large number of values can be handled. As you know, machines can remember values, not like humans. So that machines go by like how the values have been observed, and then based on that, the machine is doing the prediction. Machine learning means that we let the machine to understand the relationship. Yeah, that's right. Yeah. But the thing is that the focus is the prediction. That's all. But the thing is that you will not know the relationship, so that if you are thinking of manipulating a relationship and then using it, machine learning is out for the moment.
Okay, sir.
Good.
Okay, sir. Thank you, sir.
Yeah. Is that all? Yeah, looks like our meeting is getting more and more interesting. It's good that everybody's kind of, at least some of you, express views. It's pretty good. At least asking questions, at least asking to upload something. That's good. So can I then close it for the day? Okay, if no more concerns, let me then close
Sir,
it.
excuse me.
Oh, one more. Huh? Yes, Vasanta.
Sir, I always participate the all lectures, but December 14 and 15,
Drop me an
I
email.
couldn't.
Drop me an email. Yesterday also.
Sir,
You present
yesterday I may drop mail, sir.
Okay, right. I will check. Didn't you get a reply?
No, sir, still not get replies.
I replied to all the messages, meaning then I haven't received your message.
Right, sir, I will check it.
Yeah, okay. Otherwise, drop me a message again.
Excuse me, sir.
Who is it? Yes.
I'm Vannayaka.
Yes, Vannayaka.
I also have the same problem as
Did you drop me an email?
Okay, sir. Okay, sir. Thank you, sir.
The thing is that, you see, I told you, the most of the time the problem is that, you all don't mention, but in your case, your number is there. As long as the number is there with the name, login name, then cannot have a problem. Anyway, I will check and let you know. Okay. I will update the mark sheet and then share that again in the next meeting. Is that all? Yeah. Okay. See you in 2 weeks' time online.